Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. This is lesson 16, Converse of the Pythagorean Theorem. So we have a classwork here, proof of the converse of the Pythagorean Theorem. Okay, first let me address the word converse. All it is doing is taking the hypothesis and conclusion of an if-then statement and reversing them. So for instance, if I said, if a squared plus b squared equals c squared, then the triangle is a right triangle. The converse to that would be, if triangle ABC is a right triangle, then a squared plus b squared equals c squared. So the converse is just taking the if and making it the then, and taking the then and making it the if. Okay, so now we're going to prove using the converse of the Pythagorean theorem. So first of all, we look at these two triangles. This one's called triangle ABC, and this was A prime, B prime, C prime. What do we know or not know about each of these triangles? Well, in the first triangle, triangle ABC, we know that a squared plus b squared equals c squared. That's the Pythagorean theorem. But we do not know if angle C is a right angle. It is not labeled with this symbol here. In the second triangle, A prime, B prime, C prime, we do know it is a right triangle because of this indicator here, that that is a right angle. So what conclusions can we draw from this? Well, by applying the Pythagorean theorem to this triangle right here, we would get the length of A prime, B prime equals, or we'd get the length of A prime, B prime squared equals A squared plus B squared. So what I'm saying is the length of this side, A prime, B prime, there's no letter here, so I don't call it C. It equals A squared plus B squared. Okay? And since we're given by the Pythagorean theorem, c squared equals a squared plus b squared, then we can use substitution and replace this a prime b prime squared with c squared. And since that we have that, then we can conclude that a prime b prime must equal c. So if I have a prime b prime, the length of a prime b prime squared equals c squared, then a prime b prime must equal c. So maybe I should just say that, not skip steps. So if the length of a prime b prime squared equals c squared, then the length of a prime b prime, equals c, by taking the square root of both sides. And since it is also a prime b prime, and c is also, and now that we know that a prime b prime equals c, and c is equal to ab, then I can say if c equals the length of ab from my first triangle here, then I can conclude that a prime b prime equals ab. Okay, now let me go through this again. So what I'm saying is, if this side squared equals a squared plus b squared, that's this line right here, and we know the Pythagorean theorem is this, then I can substitute this for my c squared. So then I can say if a prime b prime squared equals c squared, because we're substituting into the Pythagorean theorem, then when I take the square root, the length of a prime b prime must equal c. And if c is equal to ab, because it's labeled over here, then a prime b prime must be equal to ab. That means that both triangles have sides A, B, and C that are the exact same length. Because we already knew A equaled A and B equaled B, now we just proved that A prime B prime is the same length as AB. And since we have side, side, side congruence, then the two triangles are the same. And therefore, angle C must be a right angle. Okay. So there is some translation that we can do, a shift to the right so many units to get B onto B prime, map A to A prime, and map C to C prime. And this triangle would land right on top of this one because they are the same size. They would line up perfectly. Okay. But if we do that, and one of them, like, let's say we can certainly perform a translation that takes B to B prime, okay, and one that takes C to C prime, because segments BC and B prime C prime are the same length. Must this translation take A to A prime? So just because, what I'm saying is, just because this side right here let me just move this a little bit, right there, that side right there. Just because I can translate this over here doesn't mean it has to land right there just because they're congruent. What if I rotated it and it was like this? Still the same length, C map to C prime, but A map to a different location that we could call A double prime. Okay, so here's A double prime. A double prime is the same length as AC because I just shifted and rotated it. Okay, then what would happen to the triangle? So here's what we're going to do. Okay, so here's what I was saying. If A prime mapped from A to a different location like this, B is still equal to B. C or A is still equal to A, but A mapped to a different location, A double prime instead of A prime. So here's our situation now. It did not map to here, it mapped elsewhere. B is still equal to B, A is still equal to A, but what happened to C and what happened to these angles? Okay. So notice that there's two isosceles triangles in this diagram. And I'm going to draw them so you can see them. I'll make one green. So there is a isosceles triangle, A double prime, C prime, A prime. So that goes from here. Oops. Okay, so here's A double prime, C prime, A prime, isosceles triangle. There's one. And then we have A prime, A double prime, B prime, A prime. Okay, so now here's A double prime, B prime, A prime. So we've created two isosceles triangles and mapping that to two different, to A prime, A to A double prime, which is a different location than A prime, using C prime and A prime and B prime and A prime as our other two vertices. Now if we label these angles and name these angles, these four angles here that we've created, then we can continue with this proof. Okay, so here's our diagram again. There's the two triangles. So we labeled this angle, which is angle C A double prime B prime W sub 1. And this angle W sub 2, W sub 3, and W sub 4. So we've just labeled these four angles that it created in the two triangles. So now we can say triangle A double prime, C prime, A prime is isosceles and therefore has base angles that are equal in measure. Okay? In other words, W sub 1 plus W sub 2 equals W sub 3. I'm going to write that over here. Okay, so this might be difficult for you to picture. What's going on here? Okay, so this is an isosceles triangle because this is length B and that's length B, so they're equal. So therefore this whole side angle, is equal to this angle. And that's why I said W1 plus W2 equals W3. Okay, see it now? So that's an isosceles triangle. And this triangle, A double prime, B prime, A prime, is isosceles because we have a side length C, they're equal. And therefore, this angle, W2, is equal to W3 plus W4 because C is equal to C. So opposite angles are congruent if opposite sides are congruent. Or if two sides are congruent, their opposite angles are congruent. So therefore, we can then say W2, W sub 2 plus W equals, not plus. W sub 2 is all by itself in this one. In that case, we have W sub 2 equal to W sub 3 plus W sub 4. Okay, so this angle plus this angle equals this angle because W3 plus W4 is opposite C, and W2 is opposite side C, so therefore they're congruent as well. Okay, so these two equations give W1 plus W3 plus W4 equal to W3. And you're probably saying, what? W sub 1 plus W sub 2 equals W sub 3. So now I can substitute this in for W sub 3. So then I would write, instead of W sub 3, I would write W sub 1 plus W sub 2. Okay, replacing W sub 3 because they're equal. W sub 3 is this. So therefore I replace W sub 3 with them. And we have W sub 3, which is this right here, plus W sub 4. Ay caramba. Equals W sub 2. Okay? And if I simplify this, and I subtract W sub 2 from both sides, then I get W sub 1 plus W sub 4 equals W sub 2 minus itself, or 0. And you're like, what? How can W sub 1 and angle W sub 4 add up to 0 degrees when each one is greater than 0 degrees? Two positive numbers cannot equal 0. That is impossible. So we just proved, conversely, that that angle C can't be a right angle if angle A double prime lays out there and that occurs. So the translation must map A to A prime, and since translations preserve the measures of angles, we can conclude that the measure of angle ACB is equal in measure to angle A prime, C prime, B prime, is a right angle. So finally, if a triangle has side lengths of A, B, and C, with C the longest length, that doesn't satisfy the equation A squared plus B squared equals C squared, then the triangle cannot be a right triangle. Okay, hopefully that wasn't too confusing to you. What are you? Okay. Okay, after that lengthy explanation of proof by converse, let's work on the exercises 1 through 7. Is the triangle with leg lengths of 3 miles and 8 miles and a hypotenuse of length of square root of 73 miles a right triangle? Show your work and answer in a complete sentence. So I would write A squared plus B squared equals C squared. 3 squared plus 8 squared equals the square root of 73 squared. Well, 3 squared is 9, 8 squared is 64, and the square root of 73 squared is 73. 9 plus 64 is 73, not 77, 73, and 73 equals 73. So yes, triangle with leg lengths of 3 miles and 8 miles and a hypotenuse of length square root 73 miles is a right triangle because it satisfies the Pythagorean theorem. And that's what you would say. So answering in a complete sentence, let me bring that in. Okay, so that's better than just saying yes. Yes, the triangle with leg lengths of 3 miles and 8 miles and a hypotenuse of the square root of 73 miles is a right triangle because it satisfies the Pythagorean theorem. Okay, number 2. What is the length of the unknown side of the right triangle shown below? Show your work and answer in a complete sentence. Provide an exact answer and an approximate answer rounded to the tenths place. Okay, so we're going to let C be the length of the hypotenuse. Okay, so the first thing I always have my students do is write the formula. A squared plus B squared equals C squared. So it's uber important to recognize the hypotenuse. The legs don't matter. I can call this A, or I could call this A, and this B, or this B. It doesn't matter. But C has to be opposite the right angle. So it doesn't matter to me if you put A as 4 and B as 1, or A as 1 and B as 4. Okay? Anyway, we'll use A squared as the base, 1 inch, plus 4 inches squared equals C squared. 1 squared is 1, 4 squared is 16, and that equals C squared. Combine like terms, 17 equals C squared. Okay? Take the square root of both sides, and the square root of 17 equals C. So provide an exact answer. There it is. And then approximate answer rounded to the tenths place. Okay, so I have my calculator here, but I do know it's 4 point something. Square root of 17 is just a little more than the square root of 16. And the square root of 16 is 4, and the square root of 25 is 5, and 17 is right next to 16, so it's 4.1 or 4.2, but let's just use the calculator. So I'd say the square root of 17, enter, 4.123, rounded to the tenths place. Okay, so therefore C is approximately 4.1 inches. Okay, and my answer in a complete sentence would be the length of the hypotenuse of the right triangle is exactly square root of 17 inches and approximately 4.1 inches. All right, number 3. What is the length of the unknown side of the right triangle shown below? So again, the opposite side of the right angle we're going to let equal C. I write my formula. A squared plus B squared equals C squared. Show your work and answer in a complete sentence. Provide exact and approximate rounded to tenths, same as last. So again, A squared, I'm going to make 6. So 6 squared plus 2 squared equals C squared. 6 squared is 36, 2 squared is 4, equals C squared. 36 plus 4 is 40, and I take the square root of both sides, and I get the square root of 40 equals C. That is my exact answer, and then I do my approximation. Now, 6 squared is 36, 7 squared is 49. This is 4 away from 36 and 9 away from 49, so it's closer to 36. So I would say it's 6.3 or 4 is my approximation guess, but I'm going to use my calculator to get my approximation. The square root of 40 is 6.3. In a complete sentence, I would say the length of the hypotenuse of the right triangle is exactly 2 square root 10, and you're like, what? Where did that come from? Okay, well, if we simplify our square root now, if we take the square root of 40 and do a factor tree, that's 2 times 20, and that's 2 times 10, and I have a pair of 2's. that goes outside the radical. And what does not, oh, that's 2 times 10, 5, by the way. And since they aren't pairs, they go inside. 2 times 5 is 10, so I put it back together. So pairs from outside, because my index tells me that I need 2. And then I don't have a pair over here, so they stay inside the radical. And you can check with your calculator. 2 square root 10 is also 6.3245532. All right. Okay, number 4. Is the triangle with leg lengths of 9 inches and 9 inches, a hypotenuse of the square root of 175 inches, a right triangle? So in other words, okay, so I always like to draw a diagram. And so they're telling us that it is a triangle with a leg length of 9 and a leg length of 9 and the square root of 175 going to be a right triangle. So the question is that a right triangle? All right, so I'm going to write the formula. A squared plus B squared equals C squared. A squared is 9 squared, B squared is 9 squared, and C squared is 175. Square root of 175 squared. So 9 squared is 81 plus 81 equals 175. The square root of 175 squared is 175. 81 plus 81 is 162, and that does not equal 175, so my answer is no. A triangle with leg lengths of 9 inches and 9 inches and a hypotenuse of the square root of 175 inches is not a right triangle because the lengths do not satisfy the Pythagorean theorem. Number 5. Is the triangle with leg lengths of square root 28 and 6 centimeters and a hypotenuse of 8 a right triangle? Show your work and answer in a complete sentence. Okay, so here's my triangle, and I have the square root of 28 here, and I have 6 here, and I have the hypotenuse of 8, and I'm wondering if this is a right triangle. So I write a squared plus b squared equals c squared. So the square root of 28 squared plus 6 squared equals 8 squared. The square root of 28 squared is 28. The square root of 6 squared is 36. The square root of, or the square of 6 is 36. And 8 squared is 64. 8 plus 6 is 14. Carry the 1. 3 plus 2 is 5. Plus 1 is 6. 64 equals 64. And therefore, yes, the triangle with leg lengths of the square root of 28 centimeters and 6 centimeters and a hypotenuse of 8 centimeters is a right triangle because the lengths satisfy the Pythagorean theorem. Number 6. What is the length of the unknown side of the right triangle shown below? Show your work and answer in a complete sentence. So in this one, the side opposite the right angle, we would always call C. So we're going to let C be our hypotenuse. And we're going to write the formula. A squared plus B squared equals C squared. A squared is 3 squared. B squared is the square root of 27 squared equals C squared. 3 squared is 9. The square root of 27 squared is 27 equals C squared. 9 plus 27 is 36 equals C squared. And the square root of 36 equals the square root of C squared, and that would be 6 equals C. So the length of the hypotenuse of the right triangle is 6 feet. Make sure you use your units of measurement. Number 7, the right triangle, or the triangle shown below, it is a right triangle, is an isosceles right triangle. Isosceles right, that means that is congruent to that. Okay, keyword, isosceles. Determine the length of the legs of the triangle, show your work, and answer with complete sentences. So I want to find A and I want to find B, but in an isosceles triangle, I know A equals B, don't I? So I'm going to write the formula A squared plus B squared equals C squared. Okay. So, I don't know the lengths of these, so let's call them x. x squared plus x squared equals the square root of 18 squared. Okay? Well, x squared plus x squared is 2x squared equals the square root of 18 squared. Therefore, 2x squared equals 18, because the square root of 18 squared is 18. To solve for x, I divide both sides by 2. And x squared equals 9. And then I take the square root of both sides. And the square root of x squared equals the square root of 9, and therefore x equals 3. And therefore the leg lengths of the isosceles triangle are 3 centimeters each. Okay, that is the end of lesson 16. Review this lesson summary and go to your problem set.